Now in this lecture we will learn the implementation of convolution code in MATLAB Simulator. So first of all, let's revise the convolution encoding a little bit. In convolution encoder we have got three registers, M0, M1 and M2, like this, M0, M1 and M2. And this is 2, 1, 2 encoder. And to get x1 we have to XOR M0 and M2, and to get x2 we have to XOR M0, M1 and M2, and then we have to put them together like this. So for that I have used the same values which I used in the slides over here. So let's assume that we have got data 1101. Our data is 1101. We add two zeros to return the encoder to its zero state. So I have added these two zeros over here in the data, these two zeros over here, and then we start the encoding. Initially, all these registers, the value of all these registers will be 0. So M0 will be 0, M1 will be 0, and M2 will also be 0. So for that case, the first iteration for I is equal to length to all the bits of message M, I have taken M1 and M2 is equal to 0, and M0 is the first bit of the message. So when the first bit of the message will enter here, so the very first bit will be here in M0, and at that time the values of M1 and M2 will be 0. Then in the next iteration, this value over here, M0 will move in M1, message bit will come in M0, and M2 will be 0. So the same thing I have done over here. M0 is I, M1 is equal to I minus 1, means the previous message bit, and M2 is equal to 0. And later on, the very first bit will be moved to M2, the second last bit will move to M1, and new bit will enter into M0. So this is M0, this is M I minus 1, and this is M I minus 2. And then we will XOR these values for x1 and x2, just as given this for over here, formula over here, equation. And then we will concatenate them, x1 comma x2, just like this. x1 is here and x2 is here. So let's run the simulation. Here you can see M is equal to 1101, and these two zeros are added into the message bit. In this, for the first iteration, I is equal to 1, this condition will be true. So the values of M0 will be the very first bit of M message bit, M1, this bit, and 1 is equal to 0, and M2 should be 0. So let's see, M0 is 1, as we can see over here, M1 is 0, and M2 is 0. For the next iteration, that is I is equal to 2, this one is true, so it will stop over here. And in this next iteration, M0 is 1, M1 is 0, and M2 is 0, because this one bit becomes value of M1, this next bit becomes value of M0, and M2 remains 0. And after that, when I is equal to 3, we will see that it will not stop here, and it should take values from here. When I is equal to 3, we see that M0 is equal to 0, M1 is equal to 1, and M2 is equal to 1 also, because this one and this one have moved to M2 and M1, and this 0 becomes value of M0. Now we see how these bits are put together. It's very simple. After XORing them, as we have seen how to XOR them before, and we just put them together to put the values at the end of every time at the end of the encoded data, 1 comma n plus 1 to n plus 2. So wherever this encoded data ends, so we will add 1 in this one, and where it should go up to 2, because we have to add 2 bits. So n plus 1 to n plus 2. This is our column value. This is our row value. Row will remain the same. We can see encoded data over here. I can run this simulation from the beginning as well once again to show you the values in encoded data after each iteration. So in encoded data, you can see the values are 1, 1. This is the output when the values in M0, M1 and M2 are 1, 0, 0. Means values of M1 and M2 are 0 and the very first bit, this 1, has entered into M0. At that time, the output is 1, 1. Now, I have to append the output values of the next output here in column 3 and 4. So, this encoded data ends over here 2. So, n plus 1 means 3 and n plus 2 means 4. So, after next iteration, I see the output 1, 0 has been appended to the encoded data. This is our second iteration, I is equal to 2. In I is equal to 3, it is again 1, 0. And similarly, every time data will keep moving and bits will keep moving and all the data will be entered. So if I want to see the final output, I just simply remove the breakpoint from here and then I see the overall output is 1, 1, 1, 0, 1, 0, 0, 0, 0, 1, 1, 1. We can also, this is I have simulated the way this convolution I had explained you in the lecture. Now, to using the built-in methods of convolution encoding in MATLAB, we can use convenc method as well to encode the same data. For that, I will use trellis method because this method convenc uses trellis input, and to get the trellis input I have to convert this polynomial to trellis, and for that I have got method poly to trellis. In this poly to trellis, the first value over here is the convolutional encoder constraint length. For 2, 1, 2 convolution encoder, the constraint length is 3. What is constraint length? I have explained you in the lecture before that the size of the window in bits is called the code's constraint length. So for 2, 1, 2, the constraint length is 3. And next, if you look at slide number 180 over here, then we can see that we have got these two polynomials, m0 plus 2 and m0 plus 1 plus 2. So here the term m1 is missing, m0 plus m2. So in that case, the first polynomial is 1 plus, this x is actually representing m over here, polynomial, 1 plus x square. So this x square is actually m2 and this one is m0. And this one, this x2 is m0 plus m1 plus m2. So that becomes 1 plus x square. So I will show you how to encode data using this encoder as well. So I uncomment this coded data over here. Let me run the example again. Now we look at the coded data. It gives us 1, 1, 1, 0, 1, 0, 0, 0, 0, 1 and 1, 1. If we want to compare the two outputs, I simply select all these values over here and put them below the coded data, and you can see that the values are exactly the same. So you can simulate or make the simulation of convolution encoding both the ways, either using this convenc method or you can use this method over here as well, which I have shown you. In this one, this one is for the trellis, for this, in fact, for these x1 and x2, and this m is the message, which in this case is 1, 1, 0, 1, 0, 0. But I have decoded only, introduced the error in this data, ink data as only, because it will generate the same output for coded data as well, because both these values are the same, exactly the same. So after introducing the error, 2 bits error, if I look at this, then I can see that I have introduced data in these 2 bits over here, 0, 0. This was 1 before error. Now it has become 0. This is 1 in coded data, and it has become 0. So error is in first these 2 bits, and the rest of the bits are the same. So let's see if this decoder is able to 2, 1, 2 is able to decode the data or not. So when we run it, we look at the decoded data, and it is 0, 1, 1, 1, 0, 0. Our data was M is 1, 1, 0, 1, 1, 0. But the output is 0, 1, 1, 1, 0, 0. So this one failed to detect and correct the data because it is beyond its capacity. In 2, 1, 2, convolutional encoding cannot detect and correct 2 bits error. Now let's try this one for 1 bit error. Now we look at the values. Then what we see is that we have got 1, 1, 0, 1, 0, 0. And our message was 1, 1, 0, 1, 0, 0. It means 2, 1, 2 has successfully detected and corrected the error. So this is how we can encode and decode the data in MATLAB. By the way, for decoding, I have used the function WIT VIT decoder, Viterbi decoder, WIT for Viterbi decoder. Here I have it placed the data. What is the type is trellis. 2 indicates the trackback depth. Truncation is the operating mode, and hard is the hard decision, because we know that in Viterbi we have got 2 kind of decisions: soft decision Viterbi and hard decision. So this is hard one, and it accepts trellis data structure. Now we will see BCH codes, Bose-Chauhdry-Hocquenghem codes. A T error correcting T must be less than 2 to the power m minus 1. BCH code has the following parameters. Block length is n, and the number of parity checks is n minus k, and minimum distance is 2t plus 1. These are the characteristics of Bose-Chauhdry-Hocquenghem. I have explained these in detail in the lectures. If you want to understand all these parameters, then you may refer to the lecture. Now, how do we simulate this BCH code in MATLAB? Code word length is n is equal to its power m minus 1, as we have seen over here. N is equal to, block length is equal to n is equal to its power m minus 1. Then k is equal to 5, message length, and m is equal to 4. And here n words is equal to 10, because we are going to generate random data over here using GF, Galois field function of MATLAB. RANDI is going to generate random integers. I is for integers, random integers in the range of 0 and 1, because we want all these integers to be binary, either 0 or 1. So we have defined the range over here, 0, 0 and 1. This is the range of random numbers. And how many such sets will be generated? 10. And the length of each message will be 5 bits. So T is the BCH number of errors, n comma k, and then we will encode it BCH ENC method, and we'll introduce noisy code, and then we will decode it. So let's run step by step. So first of all, we have achieved the k is equal to 5, m is equal to 4, and n is equal to 15. To the power m minus 1 is 15. So it is n comma k means 15 comma 5 code, BCH code. Then we see the message output. As you can see that we have got 10 pairs of 5 message bits, this the first row has got 5 message bits, then another one has got 5 message bits, and so we have got a matrix of 10 by 5. These values are randomly generated by this function randi. As I told you, I is for the integer within the range of 0 to 1. Then we calculate this t, and t is equal to 3. Now we encode the data using BCH inc method, which takes message as an input parameter, and n and k as k are also the input parameters of this function. So encoded data is in this form. I show you. You can see that we have got 10 rows, and each row, the 5-digit message has become 15-digit. After adding the parities, it has become 15-bit. Now we introduce some noise in the data, and this one is we are going to add this random error. This is random error function of MATLAB. N words, because we have to generate these 10 errors in each of the rows, and n is the value of bits in each row, and 1 comma t is the limit of the errors, which is 3. So we cannot have more than 3 errors in a row. So let's generate it, and now we compare these errors. So to compare the errors, I will just compare the last row, this 10 one. So this is 1100. Here it is 1100. Then 101. It is 001. So it means there is error in bit number 5. Then 010, 010, this is okay. 011, 101, 011 is 101. So it means that errors are in bit number 5, 11, and 12. And then we have 0, 1, and here we also have 0, 1. So we can see that 3 errors have been randomly generated in row 10 of the data. So this is what it's going to do. It is going to enter 3 errors randomly at random places in the encoded data. Now what we do is that we decode the data by using BCH decode. Using BCH encode, we encoded the data, and now BCH decode, we are going to decode the data, and it gives us is equal gives us 1, means that we have successfully decoded the data. If we look at the message received, then it must be exactly the same as this message transmitted. So we, for example, we take 11000, message transmitted was 11000. Let's randomly select 5, 11001, 11001. So in this case, we can see that it has successfully detected the number of errors and corrected them. Now, if I increase the number of errors from 3, I increase it to 4. So I can see that now I am getting this is equal to 0. It means that it failed to successfully detect the data. Why? Because we have exceeded the limit of the 15,5 BCH encoding capacity, which is only 3 errors. Now we move to our last coding method, which is Reed-Solomon coding method, RS coder. Here the message number of bits per symbol is 3, and message length is also 3, and again we have used the same 2 to the power m minus 1 to calculate the code word length. So here I have created a message using Galois field GF. These are the polynomial values, and this is my number of bits per symbol. So it must not be more than 3. So when we look at this one, X, it is 273406511. Now we have to encode this message using RS Inc. RS Reed-Solomon, Inc means encoding. So we will use this built-in function of MATLAB, RS Inc method or function to encode the data. So if we look at the encoded data output, it is this our 3-bit data has become 7-bit. 4 bits are added. So 2733676 and so on. This is polynomial. And then we introduce error using Galois field of 8. This is our remember, because we are have this 273, not just 0 and 1, because we are using Galois field 8 instead of Galois field 2. We are using Galois field 8. So it is not binary. We look at these errors over here. So we can see that we have 2, 3, 4, 6, 7 over here, and we will add this error into the code. So we look at the noisy code 0733676. Now if we compare our code with noisy code, is that our original code was 2733676 and noisy code is 0733676. So it has created error in place 2 because over here. Similarly, our code was 4064220. Now it has become 7464220. So 74 has become 40. And here we created 3 errors, 511. So if you look at this one, we have got 076 and 4540. 4540. So here we have got 1-bit error, here we have got 2-bit errors, and here we have got 3-bit errors according to this errors over here. 2, 3, 4, 5, 6, 7. So now if we decode it using the function Reed-Solomon decoding RSDEC, RSDEC, I will place this noisy data as the input and n comma k, and let's see the output. If we compare this receive code with our message, so this one, first one is okay, 273. Receive code is 273, message was 273. The next one is 406, 406. This one is also okay. But if you look at the third one, here it is, message was 511, but here it is 076. So it has been able to correct 2 errors, but failed to correct 3 errors. So if we have got 3 errors, more than 2 errors, then this decoding is not working. And this C num error, so it gives us the number of errors corrected in each row. So it shows that it has corrected 1 error because we had introduced 1 error in this first row over here. It has corrected, we can see 273. In the second row, we introduced 2 errors. We can see in errors, we introduced 2 errors. You can see over here, 2 errors in row number 2. So it shows that we have corrected 2 errors. But here it is showing -1, means it has the number of errors were more than its capacity. So it is giving us -1. A value of -1 in C num error indicates a decoding failure in that row in code. Why this failure occurred? Because the number of errors have exceeded its capacity. So now we have learned how to encode convolution coding, BCH coding, and RS coding in MATLAB. I hope this will help you to simulate more complex simulations of channel coding and communication problems.